All right, so welcome everyone again to the morning session, and it's a great pleasure to have Pawel Caputa here, and he's going to tell us about aspects of complexity.
Okay, so thank you, Onkar, and welcome everyone. I first have to apologize in advance because I just got here very late last night, and the second apologies for maybe a bit short notice about my lectures. So the lectures were supposed to be given by our two guests, Julian and Javier, that couldn't come at the end, and I was asked by Onkar to kind of replace them and and talk about some aspects of complexity. And basically, I tried to think what kind of aspects of complexity they could discuss and try to replace for them. So I'm going to be talking about basically something called K-complexity that I will explain. And this is some work that I've been doing with Javier for quite some time, and also my student Dimitris, that is in the audience. And various people over the years, but also Julian has worked on it quite a lot. So I think my lectures will have enough overlap with what I think they would talk about, if you were really looking forward to their lectures. But I'll also try to talk about some new aspects or things that I really find exciting and interesting about this topic. So hopefully it will also be original enough. And I'm supposed to give two lectures. So first lecture, this is like an ambitious plan and goal, but given the previous lecture schedule and so on, how many questions there were, maybe if I go to at least one part from the first and one part from the second, that will also be a success. But first I will start with some general motivation and goals of the program. Then I'll describe one particular aspect which stands for this letter K, namely the Krylov basis approach to complexity. And then I'll discuss some results, summarize what is known, what are kind of interesting points, mostly from the perspective of holographic applications and somehow the audience in this room. And in lecture 2, I'll discuss some of the directions. Maybe I'll focus more on holography. And then if I have enough time, I'll talk about some new application, namely studying complexity of modular evolution. And my talks will be based on a series of works that I started from 2021, and also some works in progress with these people I already mentioned. There are some nice reviews. Actually, there's an old one from, I think, 69, if I'm not mistaken, by Vishwanath and Miller on the recursion method, to just the technicalities of the Krylov approach. And there's a recent review of some of the aspects that we know already by Pratik, that should be somewhere in the audience, and collaborators. So I also send you to those two. And please stop me at any point. Maybe I ask, has anybody here worked on some of these aspects of Krylov basis or Krylov complexity? Can you raise your hand? So you know. Okay, so it's. I'll try to be pedagogical. But if I'm getting too basic and too boring, then please shout, and I'll try to speed up, or I'll talk about some more interesting applications. Okay, good. So let's start. First, the motivation. So somehow the complexity, of course, it's a really big subject on its own. But when we talk about complexity, I mean, we, in the context of quantum gravity or ADS-CFT correspondence, basically this discussion starts from the story of quantum information in ADS-CFT, of course. So one of the basic or one of the most amazing breakthroughs that we got from quantum information to ADS-CFT are some hints on the mechanisms, of course, on the ADS-CFT. So we would like to understand what is the mechanism behind the ADS-CFT correspondence. Or in other words, you can think about it like this. We want to understand how the holographic geometry can be read off from CFT. I'll be very general and kind of hand-wavy, but I guess we all share these questions and we would like to understand them better. So of course, we have learned, and maybe you have already heard last week, that entanglement understanding entanglement of CFT states is very useful for understanding what the dual geometry in holographic CFTs might be. There is also the story of tensor networks. So sometimes it's called ADS in tensor networks. When we try to think about holographic geometry as an example of somehow geometry that emerges from a tensor network that represents a certain state in many-body physics, in quantum field theory, I'll not talk much about it, but there has been a lot of nice progress and intuitions on holography that came from this, I don't know if I should call it duality, but basically intuitions about tensor networks on the dual geometry. And in particular, we would also like to understand what are the conditions for a CFT to be holographic. And by this holographic, I mean describing Einstein gravity in one-dimensional higher ADS space. Okay? And of course, there has been a bulk of work on trying to tackle this problem, trying to make these questions very concrete. And we have learned quite a lot from this, namely that of course, we still don't understand the entire story, but there are some very important puzzles. And one puzzle is that, of course, and many of these puzzles actually they have to do with black holes in the ADS-CFT correspondence and their physics. And basically, we have learned that the notion of quantum chaos, whatever that means, will play a very important role. So if we want to describe physics in the vicinity of black hole horizons, or basically scrambling properties or transferring of information for very late times, for example, then the systems, and among them holographic CFTs or many-body quantum systems that have these properties of being quantum chaotic, they share many of these properties of how black holes behave. Okay. Another important puzzle is the so-called fast scrambling. This is also probably related to that. Scramblings. And also some properties shared by random matrix theories, especially at late times, when we describe some dynamics, black hole dynamics or dynamics of quantum information at late times. These puzzles, in order to understand all these properties of ADS-CFT, these puzzles will probably play a very important role. And that's what we want to understand. Okay? So among all these discussions, I already mentioned there is still a beautiful story of entanglement, but actually, what does it have to do with complexity? So complexity came from these stories when we tried to understand these properties of holographic CFTs in two important instances, and I'll try to keep my lecture around these two, centered on these two pillars. Namely, one is the so-called operator growth. So maybe first instance is the so-called operator growth. in this context, we are interested in operator size. And what is that? So basically, we take some operator at time t, and we do the evolution with some Hamiltonian of the system. And then we can formally expand it in time in powers of t. Plus there will be other nested commutators. So maybe I'll write one more. So by operator growth, we mean that for some generic Hamiltonian, of course, most of the studies were done for in this context where we want to understand how a generic quantum chaotic Hamiltonian kind of spreads or grows the operator. But for the generic Hamiltonian, these commutators will become very complicated, even though the initial operator might be very simple. And then what we want to understand is that roughly at different, as time grows, as time changes at different powers, the operator becomes more and more complicated in terms of this, these nested commutators. And we would like to understand what is the actually effective size of the operator, size, as a function of time. Okay, how to define this size? Of course, I mentioned this was important in the context of holography. What's your question? Okay. So maybe the first important thing was that I should introduce. It was also maybe size, or it was also done in the story of so-called precursors. Where all this discussion of quantum chaos and so on also came up in ADS-CFT. And basically, it started from the works by Stanford and Schenker. That considered the setup of the eternal black hole. So here I'm drawing the Penrose diagram. The eternal black hole that should be dual to the so-called thermophile double state. At inverse temperature beta. Okay, so we take two copies of a CFT, a left one and the right, and I'm sure you have seen this picture a zillion of times. And basically, on the left side and on the right side, we have a CFT on a certain special region, and we can, for example, compute the mutual information. So let's say we have in some CFT here, let's say we consider a circle or a line, we take some interval B. Here on this side, we take some interval A. We can compute the mutual information between these intervals A and B on the other side. So, basically, from this perspective, it is non-zero because of the state is interestingly entangled. But actually, we can use this local operator. We can perturb this thermophile double by some local operator in the past. And then so basically, here there will be some RT surfaces or HRT surfaces that can be used to compute this mutual information. But if we perturb this operator at some sufficient time, when we perturb this state at some sufficient time in the past, so in other words, when we consider this thermophile double state, but perturbed by some operator at minus t omega, then this mutual information that was initially not zero will basically go to zero, and then with time evolution, let's say with left time or left minus right time, then basically there's some particular time at which we need to insert this operator that is roughly defined as a time where this and this subtle entanglement between the left and right side in the state will be destroyed by this local operator. So this was called as a holographic example of a butterfly effect, where we can put some very small perturbation in the past, but it has a very big effect on the state in the future. Okay, and then when people started studying this, it was important that basically the size of this operator or the small perturbation in the past will grow, and in such a way that indirectly it can be measured by this mutual information that it will affect the state at particular time. But how to define this size was not particularly clear. And one definition that came up of this from the studies was, of course, the so-called out-of-time order correlator. So maybe I'll define it here. So the out-of-time order correlator is in some sense an indirect measure of how a certain local operator evolves in time by the presence of another operator. And this can be computed by computing an average. So let's say I take some operator 1 at time t, and then some operator O2 at time 0, and I can compute their commutator. Well, take the thermal average for some reasons, square. Okay, so usually this average, when there is no square, it might sometimes average to 0. That's why we square it. And sorry. Yes.
Left side, and then you evolve the state. So you're saying that the operator size increases.
Right. Well, that's the intuition, that in a sense that, of course, something changes with the operator. The small perturbation has some particular effect on the state. So it's either, you can think about it from this perspective, that somehow the operator size increases. I'll try to quantify it a bit more with the commutator, okay? So in a sense that this commutator square is such that basically if you take operators that are somehow specially separated, and this commutator is 0 at time 0, then as time progresses, this commutator becomes non-trivial, and in fact it can grow exponentially. In a way where we can define so-called Lyapunov exponent for this growth of the commutator, and then later on, Maldassena, Schenker, and Stanford proved that this Lyapunov in theories that kind of dual to Einstein gravity in the bulk is maximal. So it has a particular value, 2 pi over b. Can you see what I'm writing, or it's too small? Okay, good.
Excuse me. So what do you mean by exactly the operator size? How are you defining this?
This is a part of my lecture. I'll try to define this size in a precise way.
I see. And another thing is that mutual information as you draw the graph. So what is the, how do you define this?
Oh, sorry. So how do I define mutual information? So this will be defined as the entropy of A plus entropy of B minus the entropy of the union.
Okay, thank you.
Okay, so thank you. Yes.
Which corresponds to a black hole. So, for example, in the middle of this hypothetically area space, I should not be able to see the other spot. That should be behind the horizon. And that should not. So, why
yes.
I should not have the information about the other side. Why do we have a non-zero?
Well, so here we take some subregions on one side and the other side, and the state in which we consider this entropy is very non-trivially entangled. Okay, so we don't trace the entire part. We just yeah, it's non-trivially zero. It's non-trivial at t equal to 0. It's basically just you can think about it as being computed by the geodesics, the connected geodesics between the endpoints of the intervals on both sides. Okay, so this length of geodesics basically could go through this wormhole here, and they connect these 2 points at initial times. Well, when they are non-trivial at equal to 0.
And you said that this A and B, what is corresponds to? I mean,
oh, sorry. This was some interval A here. Okay. on some special region of the CFT, and there's another interval B on a special region. Okay, so we have some CFT here, CFT left and CFT right, and this is time, and there is a space that I'm suppressing on this Penrose diagram. Okay.
Okay.
Well, so it's not like the well, I don't think the picture is that the wormhole grows, but somehow the effect of the small perturbation in the past is such that it destroys these correlations between the left and right. No, I think you can think about it holographically, but there's some particular time in the past that the effect of the small perturbation is such that it destroys this mutual information, at least in large N. Okay. Also, this is as a function of this. Sorry, I should have drawn this. This is a function of when we insert this operator in the past. Okay. So this should be this T omega. I think I draw there. In a sense that it's the effect on the RT is basically linear. It decreases linearly, so it's not a sudden jump as a function of this insertion of the operator by causality.
Hello. Is there any restriction on what kind of operator will destroy this mutual information? Like, I am sure that identity will not destroy the mutual information, right? So is there a restriction on what kind of operators will destroy it?
Yeah, well, I guess in this story it was more like a computation in a CFT where you take some typical operator, some primary, for example, that is dual to some local excitation in the bulk. Okay, so there's some assumption on typicality. If you take, and also this depends on the dimension. So if you do an explicit computation, for example, in CFTs, if you take, for example, stress tensor or some descendant, you will see that the effect is slightly different than a typical primary operator. Okay, but of course, I'm going there in some sense, but I'll try to make, this is still my very short, like general motivation. I'll try to make it very precise in a moment. Okay, and basically from this, there's also basically one term in this that you are probably familiar with, and this comes under the name of this OTOC correlator, is basically once you expand this commutator, is this correlator. This should be 1, 2, 1, 2. And basically, this correlator, in order for this commutator to grow, should decay. It's again this 2 pi over beta over t. With this is basically the same Lyapunov. Okay, so this is the out of time order correlator. But then, as you can see, somehow clearly this operator at t equal to 0, let's say for example this 1, as time progresses it has to grow, so it will affect this operator second one. But it seems like some kind of indirect probe. We always have to probe one operator by the other in order to see this thing. In other words, if you want to, you can look at this diagram. It looks more like this OTOC will. You'll have some other operator, for example, somewhere here, and you'll study some scattering in the bulk from this 4-point function. And people were wondering for a bit whether there's some direct definition of an operator size or operator, or how complex is the operator at time t. And for example, in the SYK model, this is again my motivation. I will not need much of this, much detail of the model here, but people managed to define a size as a function of t in terms of the fundamental fields of the model. Namely, you can roughly define the size operator as basically sum over the fermion number operators in the model. This will not be important. And then this size, when they computed this size of a particular of the particular operator psi I fermion in the SYK model, they indeed noticed that the average size at time t grows exponent of 2 pi beta over t. So the size was computed directly by using the operator. This Lyapunov exponent was matched precisely with the Lyapunov of the OTOC. Later, it was shown that actually at least in the SYK model, in some average way of computing OTOC and taking an average over all the operators of the OTOC, you can indeed relate this definition of the size to the definition of the out-of-time model correlator. But still, it was quite interesting a definition that people provided. So it was also some important works. By roughly the same people, but also Xiaoliang Qi and Alex Stryker, where they evaluated this size explicitly in SYK. I'll just show you the roughly how it looks like in terms of some parameters of the model. This is at some inverse temperature beta. This is some coupling. It will not be important here. And then there's this factor sine hyperbolic pi t over beta. So you can see that roughly the size as a function of t, at late times it grows precisely with this exponent here. I will come back to this in the remaining of my talk, but for the moment this is important. So at least in the SYK, one could define the size in terms of fundamental fields of the model. But the question was how can we approach this definition of operator size or operator complexity in some systematic way in all many-body models or holographic theories? Okay? 1 by n. Okay. And then why were people interested in studying it also from holography? This also one motivation was that also came up from all the studies was by Susskind. That roughly argued that if we indeed have this operator of some dimension delta of t that grows in a CFT in a non-trivial way, roughly in the bulk, this operator should correspond to some point particle of mass m. Mass m related to this delta, such that if we consider a boundary here, so there's some CFT here, I consider this excitation at t equal to 0, this operator O delta, and then I start time evolution, then there's some local particle of mass m here in the bulk, and this particle, so this is some radial direction, this particle should go into the bulk of ADS space. Of course, many people, and also in this work we mean finite temperature, so there is some black hole here. And the intuition was that the question was like, okay, so let's say that we have this operator at time t that is somehow dual to this massive particle in the bulk. as time evolves, this particle goes deeper and deeper into the interior and probes the horizon of a black hole somehow, then maybe even crosses, whatever. How do we get this information about these properties of this particle, or properties of the operator from the properties of the particle, and vice versa? And Lenny argued at the beginning, he argued that somehow the complexity of this operator, so basically when people talk about growth of the operators and complexity of the operator, they really mean the size. It's often basically used interchangeably, so size and complexity of the operator is the same. And he was arguing that somehow when there is some definition of a complexity of the operator or the size of the operator in the microscopic model, when we take the rate of growth of this complexity, it should be proportional to the particle's momentum in this radial direction rho as a function of t. Okay, this was some observation based on on the SYK model and two-dimensional gravity, and you can actually compare it with this Chi and Streicher formula. I'll try to, yes. This will be my talk. Okay. I know these are great questions, and that's where I'm going. Okay, so this is still a motivation, and basically there's the proportionality constant. This radial momentum, I'll describe it very precisely. This is a derivative of a Lagrangian of this point particle. So Lagrangian will depend on some function of rho of t, rho prime of t. Okay, so this canonical radial momentum of this particle in the bulk should be somehow related to the rate of growth of complexity. And then if we have a good notion of the size or complexity, this could be S of t, then we can test this and we can say whether this is indeed holographic.
Ordinarily, if you think about size, right now it's like a point particle.
Right.
Local operator. In naive terms, I may imagine that if you say size is increasing, I would imagine it to be a smeared operator over a region, and the volume of this region would give me the size. Does complexity eventually become something like this? Can it be visualized in this way?
Well, so this size, the way we think about it is slightly different. Indeed, like the operator here gets smeared in some particular precise way, but the point particle is not really smeared. It's still a point particle, but it just propagates in the radial direction. So somehow the image of the smearing that we have, the information that gets delocalized in the boundary by this evolution is still a local in the bulk, but just goes deeper and deeper in the radial direction. That was the intuition in the holographic picture.
It is to be understood in a different way.
Yes. Okay. But this was all, I mean, this is all very nice, and you see like there's these cartoons that you can draw. If this is really true, if we can really probe black holes, this is really amazing, because there will be some, we can consider a situation of this two-sided black holes, or maybe some particles that go beyond the horizon, maybe probe the interior. So if we can really establish something like this, we can have some microscopic definition of complexity that that gives us this relation to the momentum. This is another handle on holography, or maybe on physics of black holes. So many people took it very seriously and started searching for this definition of size or complexity and so on.
Excuse me?
Of the operators. And maybe just a spoiler, in my talk I will show you how this actually works out, and what is this prefactor here in some higher dimensional CFTs beyond also beyond the SYK in some examples, and how we can understand the relation, and what is this radial direction. It's actually also very interesting how this rho, what kind of what is this rho here in some sense. So this is kind of a spoiler of my talk.
Excuse me, I have a question. Yes.
Yes.
Okay. Am I audible?
Yes.
So actually, similar kind of analysis, there was on paper by Mark Mazie and Stanford. they had the perturbation, and basically there's a backgradation to the geometry, which is analyzed by the shock wave method. So is it a bit related to that, or is it extremely different method to that?
I'm really sorry, I could not hear well.
There's a one shock paper by where they have entanglement spreading paper.
Huh?
There's an entanglement spreading paper in which they have this particle which is basically going from the boundary to the bulk.
Yes.
And that causes a backgradation to the metric.
Yes.
Which basically is analyzed as a shock wave in the horizon. So, but in that case, I think it doesn't cross. So is the analysis somewhat similar to that, or is a completely different analysis?
I'm not exactly familiar. Well, the setup that you are talking about, it sounds familiar, but I'm not sure whether they were really computing some complexity or...
Yeah, they were, I think, analyzing the butterfly velocity. Okay, I think I will ask later.
I see. I'm not sure explicitly, except that there is indeed the particle and excitation and so on. So, okay. And so maybe the last part of this really vague motivation, but which should be somehow inspiring, is that the complexity. So this is the second part, complexity of states. And this need for complexity of states also, at least in holography, also came up with a discussion about the thermophile double state. So again, we take this thermophile double here I was talking about, and we can perform a non-trivial time evolution of this state, which can be evolved by this Hamiltonian, or it can be either evolved by the left Hamiltonian or the right Hamiltonian. Basically, this state, as you can see here, it has this property that the left minus right gives this. Okay, so in order to have a non-trivial evolution, we can actually use this left plus right Hamiltonian. This was studied by Hartmann and Maldacena, and they noticed that if you study this non-trivial time evolution, so let me call it psi of t, basically, if you study entanglement entropy, again, of some subregions on both sides, in this dynamical state, you can think about it as something called the quantum quench. You can again think about this initial state, which is the thermophile double here, t equal to 0, by being evolved in some non-trivial way, basically by flipping time to go in the same direction on both sides. And basically, if you fix the left and right time, you can look about some geodesics or HRT surfaces along these slices of the bulk that go through this interior or go through the wormhole. And basically, what they noticed is that the entanglement entropy, again, between some region A in one boundary, I think it was the entropy of a union of A and B, grows linearly with time and then basically saturates after some particular time, T star. But somehow, as we can look at this time evolution of this state, or basically interior of this state for much longer times than this saturation time, and still there's some non-trivial information about this quantum state or this geometry that is evolving with time. And again, what Susskind proposed is that, and also the original paper proposed, is that we could look at this using this tensor network prescription. So for example, if we look at this, basically at time t equal to 0, there's some kind of, sorry for my bad drawing, there's some kind of tensor network that you can think about this tensor network as basically a bunch of tensors that prepares this entangled state at t equal to 0. But as time progresses, basically this tensor network will have a part that has a non-trivial size that is related to the size of the wormhole that grows linearly with this time t. And basically, Susskind proposed that somehow this linear growth of this black hole interior should be related again to some maybe slightly different notion of complexity. So we call it complexity C of tilde of this state psi of t. Okay, so if we had another nice definition of complexity of states somehow such that it counts the number of roughly tensors, or the number, if you are familiar with some circuit model of complexity or computation, basically it counts this number of gates as a function of time, then basically this growth of the wormhole in the bulk should be related to this kind of circuit complexity of this time t. Okay, and despite this being like super intuitive and very vague, this stimulated a lot of discussions and a lot of works on trying to find how can we define the C tilde of t, and also the C of t and S of t, the size of the operators in ADS-CFT or quantum many-body systems, and whether we can see these holographic features, basically the growth of the wormhole from this definition of the circuit complexity. And I should not cross this line. I appreciate this was meant to be very kind of maybe inspiring, vague, and general, and then maybe now a roadmap of my talk will be I will now give you, with that motivation in mind, I'll give you a precise definition of complexity or definition of size of operators that came up from these discussions, and then. Somehow it often happens that you have some motivation in mind and then you stumble upon something interesting, and then this tool on its own is interesting and kind of goes in a different direction. So that's roughly what happened. Like I'll describe this definition of Krylov complexity that was originally motivated for operators, and then it was extended to states like this thermophile double state evolution and non-trivially dynamic states. And then there's a zoo of works on applying this tool to quantum many-body, quantum field theories, and whatnot. But actually, in my talk, in my lectures, I will really try to come back to holography and see where are we in this program of trying to understand holographic CFTs from that perspective of that definition. Can we really make some progress in the bulk by using this kind of new paradigm for computing complexity in many-body systems to say something about this momentum of the point particle or the growth of the wormhole? So that's my plan.
Say something about the crossover time where the entropy saturates?
Yes.
Time.
So
Typical times in chaos.
yeah, so usually this saturation is related to the size of the interval of which you compute it. It's because this is for, at least in this particular setup of quenches in low dimensions where you can really compute it. It really is like it goes as the size of the interval A that you choose to compute it for. So it's very fast. Basically, the information, you can think about it as in a quasi-particle picture. The information, there are some quasi-particles inside the region, and once they leave the region, roughly this is where the saturation happens. Right. In some explicit examples, like this is actually never sharp. Like if you take a large C or large N holographic model and you compute it by some dominance of surfaces, this is actually a sharp line. But in some explicit many-body systems, it becomes more round and so on. But time is of further, by causality, is of further the size of the interval. Whereas the times for which you can still use this classical description of a black hole and the size of the wormhole growing is much, much larger. It's like exponential in the end.
Uh, I have just basic question. Um, can you define just what is the major difference between chaos and complexity? Because some of the tools that are being used, like OTOCs, OTOCs, they are using quantum chaos nature as well, and they measure the scrambling. So how would you define the differentiate between chaos and complexity?
If I understand the question, how will I define? Well, so the questions we are okay. So the questions we will be asking is, for example, what are the proper? We'll try to find. The goal is to find some definition of complexity in many-body system, and we'll try to see how this definition looks like or how it grows with time in systems that have chaos or that don't have chaos. Okay. So basically, maybe one of, for example, this out of time order correlators, we'll see that they grow or decay exponentially in systems which have chaos, and will oscillate or something like that in systems which are not chaotic. Okay, I don't know if this answers your question, but it's I mean the chaos will be somehow the property of the system, whereas the complexity will be question about certain observables or maybe evolution of states, for example, in those systems as well. But
Yeah. Okay, I got it. Thank you.
Yeah. So if I think of in the first picture as some mass particle going to the horizon, then it will deviate from the null line, right?
Yes.
Towards the horizon.
Yes.
And that parametric length, can you tell about the complexity where this massive particle hits the horizon and then the null ray that hits the horizon, the difference between that parametric length, could you tell something about the?
I don't know. I haven't thought about it. Definitely we can, there's a nice part of this picture. If you believe it, if you think that this is intuitive and so on, if you like this picture, you can see that there's already from this formula, you can see that there's a certain time, let's say in Schwarzschild coordinates, between sending this particle and particle reaching horizon. And this time is basically roughly beta over pi, beta over 2 pi or something like that. So you can see that the size, at least in the SYK model, you can see the size starts growing exponentially after that time. Okay, so basically the exponential growth of complexity is related to particle being in the near horizon region. I will make this very precise as well in some practice. Sorry? Role in. Okay, well, I guess by now you can use them as a definition of quantum chaotic properties of a system. At least if the system has a very large number of degrees of freedom, there's some separation of scales between, say, beta, the collision time, and the so-called scrambling time, which is basically log of the number of degrees of freedom. In those systems, there's a proof that the value of this Lyapunov exponent is bounded from above. So if the system is quantum chaotic in a certain precise sense, then this Lyapunov tells you how. So you can think about it as a different definition on top of, for example, spectrum of the model and so on. That's one role. If you're asking about the role in holography, so in holography, there will be some scattering in the bulk, as I was trying to draw here. And basically some properties of the scattering of objects in the vicinity of the black hole horizon will have something to do with this Lyapunov exponent. In fact, in Einstein gravity, there is some exchange of some spin 2 particle that is dominant in this so-called high energy, some Regge scattering, and then this has to do with this exponent being maximal. But I will not talk about it. I will focus on more on the size and then complexity of states.
So in SYK, what is the motivation behind taking the sum over psi as your size?
What was the motivation?
Yeah. I can define 4 point psi as, I mean, psi.
Well, it's roughly the number. So, okay, so if you, in some models, when you compute these things for some particular Hamiltonians, and maybe if you take averages, you will notice that basically these operators that appear on different powers of t, they are just strings of different size n, okay? So basically this psi is like an average length of a string in this model. I think you can motivate it that way. Okay, good. So can I just erase now? Or so now I'm going to go to a very precise, so I'm going to kind of switch to a different area. There will be nothing about holography for a bit. Okay. Now let me talk about this Krylov basis approach or Krylov complexity. Okay, so what I'll be talking about now is basically how from all this motivation over the last, I don't know, maybe already 10 years, we managed, I mean, we, like the community, we managed to kind of narrow down the set of questions that we had from holography and also from many-body system to a very precise setup. And we came up with a kind of paradigm or a definition of a definition of quantifying complexity, and it is super precise. So let me describe and technical. Let me describe this now, and then we'll see how much we can say about this nice gravity story. So good. So let me consider a state again, some time-dependent dynamics with some initial state psi 0 at t equal to 0. For the moment, I'll be talking about the states, but I'll after I explain everything for how the construction works or how the definition of complexity works for states, it will be very simple to explain it for the operators as well. So now I'm really going to talk about these two stories. But for concreteness, I will also write, this will be our setup. And we are interested in quantifying as time grows, how to define a notion of complexity of this state psi of t or the operator O of t at particular value of real time t, okay? And this will go, I'll describe this for states, and this will go through something called the Krylov basis. Which is actually super simple and intuitive. So what we do is we formally take this state and we expand it in the powers of time. Okay? Here I'm taking, this is arbitrary, but as you can see, there are two ingredients in the story. There is this initial state for which we'll perform an evolution, and of course there's a Hamiltonian age, okay? So once you give me these two things, I can just define the state like that and expand it in powers of t. And then you see from here that actually these states, Hn, n power of the Hamiltonian acting on initial state, of course they are not orthogonal, They are not orthogonal, but actually they define something called the Krylov subspace. What is Krylov subspace? Of course, the Krylov subspace will be just some initial state psi 0, or you can think about it as initial vector and some arbitrary powers of a matrix acting on it. So there will be one Hamiltonian on psi 0, two Hamiltonians on psi 0, and so on. Okay? And what we would like to do, we would like to write this as sum over, I will use n, but it will be maybe abuse of notation, some dimension, some wave functions psi n of t, and some basis kn, where now this kn is an orthonormal basis. And the dimension here, it will be dependent on the properties of the Hamiltonian as well as the properties of the initial state. Okay? So this is a definition of a basis and its coefficients. And how are we going to do this? We'll apply something that you learned in your first course of algebra. We will simply do a Gram-Schmidt orthogonalization. Okay? So we'll take this Krylov subspace and we'll recursively try to build a basis using Gram-Schmidt orthogonalization step by step. Okay? So this is a definition. This psi n of t will be some wave functions. I will tell you how we compute them in a moment. Recursively for each power of n. Okay? Function of? Well, generally, you mean position? Yeah, generally it will be also a function of x and so on, but here we are just interested in this time evolution, okay?
Hey, Kn is the basis of the Krylov subspace, right?
So the Kn will be, I'm going to define it now. Okay. It will be a basis obtained on this Krylov subspace, okay? Good. So how do we obtain this? There is a name for this. It's called the Lanczos algorithm. Which is, you can convince yourself that this is nothing but the Gram-Schmidt orthogonalization, okay? We choose K, we start with n equals to 0. We choose K0 to be your initial state. Okay? We choose it to be normalized such that psi 0 is 1. Okay? And then we'll define first a vector a n plus 1 as n kn minus bn k n minus 1. Okay? With the definition that for n equals to 0, b0 is 0. And then we introduce the normalized vector kn to be simply bn to the minus 1 times an. Okay? Where in this definition, this so-called Lanczos coefficients an, they will be defined as an expectation or value of this Hamiltonian h kn, and bn will be simply a normalization of these vectors an. Power 1/2. Okay? You can convince yourself that, for example, if you take A1, just on the side here, if you take A1, this will be just Hamiltonian minus A0 acting on K0. Okay? And you can check that if you do the Gram-Schmidt orthogonalization, this guy should be orthogonal to the previous one, to the K0, which fixes for you A0 as an expectation value of H. And then once you normalize it, it will be just this B1 coefficients. And it goes like that step by step. And one thing that is that you can quickly notice is that by definition, you can write this guy as simply B n plus 1, K n plus 1. So what this basis does for you is you can reshuffle these guys to see that Hamiltonian acting on this Krylov basis as simply a diagonal piece plus Bn K n minus 1 plus B n plus 1 K n plus 1. Okay, so if you compute matrix elements of the Hamiltonian in this basis, so Kn, K, H, Km, you see that it becomes tridiagonal. You'll have these Lanczos coefficients on the diagonal, and off diagonal there are these B's, B2, B2, B3, B3, and so on, but everywhere else is 0. Okay, so this is a particular basis where the Hamiltonian has this form. And I also have to tell you one important thing. You continue this construction up to n equals to n star, where b n star equals to 0. Okay, that's where you stop the procedure. You cannot construct any more orthonormal states from this infinite set of vectors. Okay, and this will be crucially dependent on the initial state psi 0 as well as on the Hamiltonian. And what else? Yeah, basically, that's the definition of the basis. And once you construct this basis step by step, you end up not only with the basis, but also with the set of coefficients, ANs and BNs, okay? This is like the outcome of this Lanczos coefficient. There are some systems I will talk about, not sure if today, that these ANs and BNs, they can be infinite and so on, but typically for finite dimensional Hilbert spaces, this will terminate, it will be bounded by the dimension of the Hilbert space or depending on the operator by some other. Okay, and then the important question is, this is not the end of the story, how do we determine these coefficients? So basically, as you see, as we defined, this is just, and this is our state again, sum over n psi n of t kn. So if we hit this with the derivative, this is nothing but h of psi of t, but this is of course also, so we can write it as a sum over n, I, the derivative of psi n of t kn. On the other hand, this is sum over n, psi n of t h on kn. And we're going to use the definition of how the Hamiltonian acts on this basis. And once we reshuffle, we can reshuffle it such that we write everything under one sum. So we can write sum over n, an psi n of t plus bn psi n minus 1 of t plus b n plus 1 psi n plus 1 of t kn. We end up with the Schrödinger equation for these amplitudes. that we have to solve with the initial condition that at psi n at t equal to 0, we should be at our initial vector, which is k equals to 0, which is nothing but the delta function n 0. Okay? And so basically, this is the algorithm to expanding any dynamics. I have not assumed anything about the dimensionality and so on, but we can effectively expand any dynamics into a one-dimensional evolution on a certain chain that is labeled by this indices n. And this is what this Schrödinger equation describes. So basically, we can think about the chain that is labeled by these n's. So this is some phi 0, phi 1, phi 2, phi n minus 1, phi n plus 1, and so on. And such that this dynamic, the probabilities of if you are at some site n, and the probability of staying on this site is basically given by an, but probability of hopping to the right is given by bn plus 1, and probability of going to the left is given by bn. So this is like some effective one-dimensional Markovian dynamics in this system. And
excuse me. So if your Hamiltonian is time dependent,
yes,
then the I mean the states, I mean h minus a and something, that will become, I mean even the coefficient n becomes time
this
dependent.
will become
so
time dependent.
There should be some extra time appearing.
So here everything I'm talking about is time independent.
Okay.
Yes, that's an important point. But you can make some progress also on time independent Hamiltonians.
Nice.
Yes.
Thanks.
Well, canonical, I'm just giving you a setup for arbitrary questions you might have of this type. Say your questions that you are interested in is like, this is my initial state. I want to do the unitary time evolution. How do I quantify the complexity of that state or the operator? Okay, so sometimes this question might be very simple if you choose very simple operator or very simple initial state, and the algorithm, everything works in such a way that it will give you a simple answer. So exactly, this is very much tailored to the initial state and the Hamiltonian. It's a very important point. Okay. No, so it doesn't have to, but if the Hilbert, like this is just a basis, okay? So it's always bounded by for the states is always bounded by dimension of the Hilbert space, okay? You can of course expand this in energy basis or whatever, right? Like the evolution. This basis is such that it's particularly chosen, okay? I can make some more comments on that, but yeah. Okay, and so what do we do? So this one-dimensional picture, you can think about it as basically the initial state. So basically here we have this initial state here. I will tell you in a minute. You can also have this initial operator at t equal to 0, but as time progresses, you are kind of moving to the right on this one-dimensional chain, and you need more and more new Krylov basis vectors which have higher powers, at most h to the n acting on the initial state as you proceed to the right. Okay, so this is one directional basis that the more time passes, the more complicated Krylov basis vector Kn you need to put to describe the evolution of that state at particular time t. But in particular, the basis is created in such a way that it supports the evolution of the state for any t. Okay. I will show you some examples, but the important point is that so basically based on the unitarity, we can define the probability distribution by simply taking these coefficients psi n of t okay, and this probability distribution. So all this set of probabilities for given n's, they have the entire information about the dynamics of the state or the operator, and they tell you where on this one-dimensional chain you are at time t, okay? And indeed, we can define an average n, so to say, on this one-dimensional chain, and this will be called K complexity or spread complexity of the state as a function of t, by simply summing, by computing average position on this one-dimensional chain with this probability distribution Pn of t. Okay? And yes. 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 That's a comment or a question? Oh no, this is, yeah, I agree. This is like this. So you start with in this one-dimensional picture, your initial state is very simple or whatever. It's always at the origin, and then once you evolve it, you expand it in some particular basis that is graded by how many powers of the Hamiltonian you have to use, and then the position on this one-dimensional chain is what we call the size or of the state or the operator or the so-called spread or Krylov complexity. Okay. I will show you in a little bit, I will now quickly talk about the operators, but I will show you how this generalizes this idea of the size in the SYK model and how this can be applied to arbitrary numbers.
Sir, am I audible? I had a question. I'm talking online actually.
Maybe, yeah?
Yeah, so just related to this, you have written spread complexity as average n, which is basically the support of my current state over the Krylov space.
Yes.
But we know that after, say, log n of the dimension of the Hilbert space, all these Krylov operators are approximately maximally entangled. So what does it mean to be supported by certain Krylov operator, Krylov basis rather than other? I can just permute them and just write them again, but would that mean I would be on the different support?
No, yeah, I think what you're saying is correct. So if the Hilbert space will be finite dimensional, the properties that you are talking about, they will be reflected in these properties of ANs and BN Lanczos coefficients for late times or for very large N's. Okay, and we can see that for initial times they have a certain profile, scaling with N. Then as time progresses, they can become constant or they can go to 0. And then this average size or complexity can go down to 0. Okay?
Yes.
Or it can reach, and it can indeed reach a constant. So this will be roughly what you're saying, that all of them will be equally spaced or distributed. But the point is that it will still, you can still represent it on this one-dimensional picture. Now I will show you some examples how this motion on the picture on the chain looks like. It can be equally distributed on the entire chain for very late times, or it can go to the right and turn back after some time, and so on.
Yes, sir. That is for the coefficients. But if I look at the Krylov basis itself, the basis, all these basis vectors are maximally entangled. If I were to see a subregion, and then I can define whether it is maximally entangled, and that happens after all the Krylov bases which are of log n, say where n is greater than log n of the dimension of the Hilbert space. Yes. So in that sense, say suppose K2, K3, K4, K5, all of them are maximally entangled, and there is no way to differentiate among them other than just they came because of this Langkos algorithm. Yeah. So in that sense,
they will always have a different power of. You can always differentiate by different power of the Hamiltonian. To be honest, I think it's a great question. I don't exactly know because this setup is quite general. I don't think there has been an honest study of showing what is the pattern of entanglement between different Krylov basis vectors. And that's what you are talking about. Maybe you have some intuition on this for the operators, but I'm not aware of like a systematic study of that, whether the entanglement really increases and so on.
Yes, sir. Thank you, sir.
The complexity is defined as the average position on the chain. Okay, so the farther at t equal to 0, you always have complexity 0 by definition. And then the farther as a function, so this complexity, it will be a function of time, okay? There will be some operator. And basically the farther from the left or from the starting point you are, the more complex the state is in some sense. But the average position, it will be one quantification of complexity. Maybe this is also a good point to add that basically here I just show you how to map any dynamics to this probability distribution Pn. And of course, I'm picking up one definition of what kind of information I want to extract from this probability distribution. There is more, of course, there are other moments and so on. There's another quantity which is very nice, which is called K entropy, which is of course nothing but the Shannon entropy of this probability distribution Pn of t that you had on the previous lecture. So this will be just sum over n Pn of t log Pn of t. And this is itself, it can be also studied to quantify this dynamics on the 1D chain, and there has been some nice stories in that. I will not talk much about it, but that's a nice quantity. Okay, very good. So now let me go to the operator. So what do we do? How I told you that we can define complexity for states and operators in some, we are interested in defining complexity for states and operators, and now I will tell you how to use this definition construction to kill two birds with the same stone. So, and actually the definition for the operators was actually the first one, and due to Parrikar et al. As well as, I would actually date it back to these papers by Chi and Stryker and Stanford and whatever for the SYK, but basically what they pointed in this nice paper is that this evolution of the operator that we wrote there, it can be nicely written as the evolution using the Liouvillean operator. And what is the Liouvillean? Liouvillean is just an operator, the super operator, so operator in the space of operators. When it acts on something, it takes the commutator with the Hamiltonian, okay? So in such a way that all these nested commutators, where I write sum from n to infinity, it to the n over n factorial, you can think about it as the different powers of the Liouvillean acting on this initial operator. Okay, so you have operator 0, the first one is the commutator, then commutator of the commutator, and so on. These are just different powers of this Liouvillean acting on the initial state. But once I write it in that way, I can apply, now this will be my Krylov subspace. So I have an operator at 0, Liouvillean on the operator of 0, and so on. Now this is my Krylov subspace. So I can apply the Lanczos algorithm straightforwardly for this Krylov subspace, the same as I was explaining. But there is one more step that you need for the operators. And basically what you want to do is you want to map this after you have applied this. So indeed you can just write an operator, again, as sum over n, or there's a convention in the literature of writing these amplitudes with some I in front in terms of some basis of operators, okay? But what we need is we want to introduce a Hilbert space in which this Liouvillean acts on this state like this, or in other words, in which we can write this like that. Okay, and this is usually done by the GNS construction. Think about it like this. So in other words, we take this operator 0, and we associate it with some state. You might have noticed that I'm writing some curly notation here, and also Liouvillean acting on O0. We can associate it with a Liouvillean 0 state, which is O1, roughly with some normalization B1. And for that, we need to choose an inner product in a space of operators. And there is a standard choice that we've been using for the years, which is basically a Whiteman inner product. What is it? Basically, we'll take the inner product be the thermal two-point function. Where by this, I mean just 1 over the partition function trace e to the minus beta h. There it is. Okay. And after I have chosen this inner product, I end up with the same problem that I had there for the states. So basically, there is a yeah, I can basically repeat this analysis there. I want to map now the Liouvillean, this basis of operators ONs that I'm writing here will make my Liouvillean tri-diagonal and so on and so forth. And then I'll have a one-dimensional chain on which this growth of the operator will be represented as by this probability distribution that satisfies the same Schrödinger equation for the operator moving to the right. Generically, of course, you can study this for any operator. So the operators might be not Hermitian and so on, and you will have to go through that procedure there. But actually, if you want an operator to be an observable, evolution of the observable, then you will have certain symmetry, basically of time reflection symmetry in this setup. And this basically requires that this, for the operators, Lanczos coefficients, ANs, they can be set to 0. Okay, so basically this Schrödinger equation in most of the papers on the evolution of the operators, you will only see this Schrödinger equation with the BNs and not ANs. Let me write it here. This one? This one? Oh, so this is now the Krylov subspace. Krylov subspace. So here I started my Krylov subspace for the state was basically the initial state and all the powers of the Hamiltonian acting on this. For the operators, it's the same story. It's just an initial operator at 0 and all the powers of the Liouvillean acting on this one. Okay, and then if you choose this inner the Whiteman inner product, then there will not be generally orthogonal, and you need to apply Lanczos algorithm to find this basis of operators or basis of states to rewrite this this state from these guys here. But once you have done this, again, you have a probability distribution Pn of t, which is phi n of t square. And for this probability, you define the operator size. So basically, operator size as you can call it size of t or complexity of the operator or k complexity of the operator. There's a lot of notation in the literature as sum over n and Pn of t. Okay?
Sir, I had just one question regarding this operator to state mapping. There have been other mappings also used like choice isomorphism
Yes.
and the vectorization. So
Yes.
has there been any studies where we have not used the thermal isomorphism but the Choi isomorphism to map the operator to a state for this Krylov complexity definition?
Yes. I think there is a lot of studies of how you can generalizations of how you can choose different inner products. You can also choose this vectorization, but the idea will be the same. Once you have represented this operator as a state, you just want to rewrite it in the Krylov basis that way.
Okay,
Some of this maybe Pratik can correct me if I'm wrong. Maybe some of this is described also in your review, the different choices and vectorization, right?
So just one
maybe different vectorization as well.
So just one additional question. This thermofield state that we have defined to this vector, this isomorphism, it is majorly not maximally entangled and may not be a convex set. But if we were to take that Choi isomorphism, we know for sure that it will be a convex and a maximally, it will be a unique set. So in that case, will it give any difference in the operator to state mapping, or will it be same?
Sorry, I'm not sure if I understand. Did you hear properly? if instead of using thermal state, we use the maximally entangled state. Yeah, I'm not sure. I think this has to be studied case by case, I think, because this depends on the operators and so on. Okay. Yes, right.
Hi, Pavel. It's Bhaskar here. So just one question, since you're talking about this operator growth, there's also one similar like eigenstate thermalization hypothesis. So in this is like operator growth hypothesis answer to that ETH, that thermalization happens because the operators are growing, or like is it an answer, or does it tell us something different?
Okay, so you're jumping a little bit. This first part I only
Sorry.
described. No worries. I only described like what is the setup and how do we define this quantity. I think next lecture I'm gonna show you what are the known results depending on the various Lanczos coefficients and for random matrix theories and so on and so forth. So this will be a part of my second lecture.
Oh, okay. Thank you. Thank you.
Do I have a minute or so? No, I should finish. Can I, before I take a question, can I just, because if I define this thing, then I think this will be as much as I wanted to cover, and then I can take your question. Okay, so basically, I hope you appreciate the simplicity of this definition in some sense. So we map any dynamics into this problem, and then we really need to solve this equation. Of course, you know, there's no free lunch, so at the end of the day, in most interesting cases, you will have to solve this question numerically, and these ANs and BNs will be horribly complicated and so on. But in principle, if I come to you and I give you these Lanczos coefficients, you can plug them and solve it from the computer, or in some cases analytically, as I will describe. But this is kind of the meat. Like if you solve this, you found the probability, and this probability describes the entire dynamics. There's no more information about this dynamics than it's hidden here. But it might be horribly complicated. But when you see that these Lanczos coefficients are the key, okay? And how do you find them? So there is a kind of shortcut. You can also see where this information about this story is hidden. There's a shortcut of finding the Lanczos coefficients, and it comes from something called the return amplitude. Or the Lanczos amplitude, or the Log-Schmidt amplitude, or Log-Schmidt echo amplitude, sometimes called, which is basically this quantity that is the probability amplitude of doing a time evolution. Okay, this is also sometimes a matter of convention. Usually in our works we put plus here, but you might find a minus here, doesn't matter. Which is a probability amplitude that you do the evolution and nothing happens, okay? So you just do a time evolution and you project on the initial state. And once you find, so basically you can rewrite this in the Krylov basis. This is, of course, we agreed this was K0 e to the IHT K0. And basically what is interesting are the moments of this, okay? So basically we can expand this guy in moments that I define this way, where the moments will be the derivative of this return amplitude with respect to time at t equal to 0, okay? And what do we get from this? Well, you can see that these moments, again, they are nothing but the expectation values of the nth power of the Hamiltonian in the 0, 0 vector, okay? And what does it mean? I showed you there that basically in this Krylov basis, the Hamiltonian is tridiagonal, okay? So what you do is like you take this n by n tridiagonal matrix, and you take some size of the matrix, some size capital N by n tridiagonal matrix. You take the power n of that matrix, and you look at the 0, 0 component here. Okay, And this 0, 0 component is related to the nth moment of the return amplitude. This can be done in a very nice algorithm, which has to do with counting something called Dyke paths. And basically, it just tells you that irrespectively of any dynamic, this is purely kinematical, the moment's ends will be polynomials of these Lanczos coefficients, A0, B1, blah, 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 okay? So step by step, you can also, by knowing, because these return amplitudes are usually physical objects that we compute, that we measure, and so on. So once you come to me and give me this return amplitude and its moments, I can solve these polynomial equations and find Lanczos coefficients from the moments explicitly, okay? And after I found these Lanczos coefficients, I can just plug them to that equation and then solve it. So that's somehow how there's a shortcut to this Lanczos coefficients, or to that equation, if you know the return amplitude. And basically, it's kind of nice way of picturing this this algorithm or this Dyke paths. So let me just call it here. This will be some moment. This will be 0, mu1, mu2, mu3. You can find this. This is some kind of nice computer science algorithm that we'll use. Draw one simple example here. So basically, every time you're on the horizontal, in my conventions, you have on the axis A0, I times A0, I times A0. On the first line, you have I times A1, I times A1, here I times A2, and so on. And off diagonal, this is IB1, IB2, IB1, IB1. This is IB2, IB2. And if you're interested in moment, for example, let's do the simple one. If you're interested in the first moment, you can see these moments are defined as a number of possible paths starting from the origin to reach the given moment mu1. So here you can see that mu1 is nothing but I times A0, and every time we cross the path, we multiply the weights of this path. So for example, for mu2, you can go two ways. You can go this way. So mu2 will be I A0 to the power 2, or you can go up and down, plus I B1 to the power 2, and so on. So this can be nicely done in a computer to, once you come with the moments, then you can solve the Lanczos coefficients. And then this is my last point. Why is that interesting? Because we are more used to thinking about, so what are the moments? Notice that the moments are really the expectation values, the nth expectation values of the Hamiltonian in the initial state, okay? Basically I to the n, a to the n, psi 0. So if you want to, sometimes if you want to extract physical information about the Lanczos coefficients, you want to think about these moments. And you can, for example, check that, well, this A0 is nothing but I times, I A0 is nothing but psi 0 h psi 0. But interestingly, if you solve it, B1 square will be psi 0 h psi 0 square minus psi 0 h square psi 0. Okay, so this will be a variance of the Hamiltonian in the initial state, and I will use it. I will use this. This is true for arbitrary initial state and arbitrary Hamiltonians. That these Lanczos coefficients are related to the average energy in the initial state and the variance of the energy in the initial state. And higher powers, they give you higher moments as well. But I will use it in the rest in my second lecture. Sorry. Or this one, this initial. Yeah. So I think that's maybe there's a minus sign or difference. Maybe Maybe there's an I in my definition somewhere because I'm using I as a definition of the square. Okay, good. So that's all I wanted to say today.
States, at least in the Schrödinger picture, such that if I took an eigenstate as the initial state, then the complexity goes to 0. That seems to be the definition.
It becomes very simple. So you, for the initial state, you can see that it's indeed the phase, and you will only need the initial state. You always need it, and maybe yeah, that's where the algorithm stops, or you will need one more. Maybe I think if Hamilton expedition of Hamilton is non-trivial in the state, that you will need 2 states basically for the eigenstate.
So staying within the Schrödinger picture, if I did an evolution for the density matrix, for example, what is the similar statement for operators? I mean, what is the density matrix state which has the minimal complexity defined this way? For states, it's clearly an eigenstate, or the set of all eigenstates which has the minimal complexity. So what is the corresponding statement for operators in the Schrödinger picture evolution?
Well, of course, you can take a density matrix by just taking 2 eigenstates, a pure density matrix.
Okay, I mean, yeah, okay, that's a
but for this depends on the system. Well, yes, it will commute with the Hamiltonian. But I think you're asking about some non-trivial ones that maybe has 2 vectors or something like that. So that really depends on the system. For example, you can take a Pauli matrix, some sigma x, and then some simple Hamiltonian, in which this Pauli matrix will be very, by commutators will be very simple, right? But if you tweak the Hamiltonian to have non-trivial commutator terms with sigma z and sigma y and so on, then even the simple operator will grow non-trivially. So the question you're asking is not only, there are 2 ingredients always. It's in initial state or initial operator and the Hamiltonian.
Yeah, I understand that. So, which is why I was trying to ask, for any Hamiltonian, clearly an eigenstate would work in this construction.
That's right.
So similarly, for any given Liouvillean, which need not be a closed system dynamics, say it's a Lindblad, for example, for any given Liouvillean, is there some statement about the minimal complexity operators is what I was asking.
Yeah, not that I know.
For instance, in free theories, there are creation and annihilation operators.
Yes. So it's model dependent, I would say, but maybe there might be some story there. Sorry, from you're saying from the graph theory. Is this a solved problem? Yes. Yeah, so there's an algorithm you can recursively do for any n to write, mu ans and bns, relation between ans and bns and mu-n's. This is a combinatorial algorithm that I was trying to graphically only illustrate.
I have 2 questions. One is, so you start from the expanding exponential, but it's just like expanding the exponential, for instance, you can expand the Bessel's function, for instance. So what's the point you expand in this specific way?
In this specific basis?
Yes.
Well, of course, this is part of the definition, but at least in some cases, we managed to show that, for this question, you see that you will not, if you expand it in the powers of the Hamiltonian, you will not generate any new states than just Hamiltonian acting on this one. Of course, it might be a trivial statement because Hamiltonian may be very complicated, and anyway, you will have that. For operator, maybe it's more clear in a sense that if you will never generate more complicated operators than the commutator of the Hamiltonian with the initial operator and the nested commutators. So there might be some interesting operator in the theory that you will never generate by this evolution. But what we managed to show is that, at least actually proof for the states, is that if you start with the initial state and you start building up the basis recursively, you can choose any, as long as you choose the basis that has this initial state as your first vector, and you choose, you can choose your favorite basis, and you can find a cost function that you can minimize, which has very mild assumption, basically such that it assigns some weights to the states with higher numbers of Hamiltonians that are not decreasing. Okay, so if the state has n powers of the Hamiltonian, the cost will have like n to some power, and we prove that minimizing over such cost functions over all choices of the basis will be achieved by the Krylov basis. Okay, so this is the, I don't know if I mentioned the paper with Vijay and Javier and so on, where we showed that the Krylov basis is the minimum over all choices of the basis. That's one way of defining Krylov complexity. You can choose any basis with this initial state, project this state on that basis, and then minimize over all choices of the basis. I know it sounds complicated, like this is what quantum information people like to define, but in practice it sounds complicated. But if, for example, if you have discrete time dynamics, you can easily prove that the Krylov basis will be the one that has the minimum with this choice of the cost function that we show.
Thank you. And when the time, the second question is when the Hamiltonian is time dependent, naively Krylov basis depends on the time, and that's something we don't want. Yes. So how do you avoid that?
Well, why do you say that the Krylov basis has to depend on time? Why can't you just put it in? Maybe there might be some scenarios that you can put it by some smart choice of just to Lanczos coefficients and not to the Krylov basis. But even though, like, I don't know why. I mean, actually, on the contrary, I don't know why it might be actually very interesting to study the time dependence of the Krylov basis as well, because then basically this, if you take this, when I was deriving this the Schrödinger equation, if you take time derivative with t and you have a basis dependent, basis depends also on time, then there might be some non-trivial effects like Berry phases and so on that will be entering that Schrödinger equation. So I think that would be a nice problem to study in detail.
Any other questions?
Hello, Pawel, Bhaskar here. So just one question related to scrambling. So you said that Krylov complexity basically detects the scrambling, and OTOGs also detect the scrambling. And some people say that Krylov is a more sensitive diagnosis of scrambling. So can you tell me, like, what makes it so sensitive? Like, even for some systems, when OTOGs fail to detect the scrambling, Krylov does that.
Yeah, I'm not sure that's true.
I've heard in some talks, like, maybe.
Sorry?
I've heard in some talks, like, they said that for some systems, when OTOGs are not diagnosing that scrambling, Krylov does that. Krylov is able to diagnose the scrambling aspect of it.
I'm not so sure about this. Like, in a sense that I think both are very important. Maybe I can give a short answer. So there has been some nice progress on understanding this a little bit more. So of course, from the field theory perspective and so on, 4-point functions will always know more than 2-point functions. So when you have some non-trivial dynamics, so if you define if you define out of time order correlators and some quantities there, if the system is maybe, I don't know, random or maximally chaotic, maybe there is some, these numbers will be the same because roughly you cannot tell the difference. But generally, I think 4-point functions should be more sensitive. But there has been some nice way of formalizing it in a sense that I told you that these operators of t that we wrote in the Krylov basis, they can be defined as this, basically these coefficients here, times this operator ONs, okay? Then where these are the Krylov basis operators, which we construct by Lanczos algorithm of operators. And it's very instructive to, for example, write the OTOG that we were writing. Oh, this is usually dagger. Nothing stops you from expanding this OTOG in this basis. So you'll have some sum over n and m, phi n bar, phi m t. There will be some factors of I, that whatever. And then here you'll have this On, O2 of 0, OM, O2 of 0. Okay? So basically you see that here the out of time order correlator can be written in terms of some interesting kernel, which is basically this four-point function of two operators that were at initial time, and then two of these operators from the Krylov basis that you constructed. This is an identity, okay? And sometimes it's, so basically this was dubbed to something called the Krylov metric or something like that, okay? And sometimes it might happen that indeed this object here might go like nm times delta nm in some scrambling or chaotic systems in such a way that basically this thing just becomes the Krylov complexity. Okay.
Okay.
But generically, there will be more non-trivial information about how these operators in the Krylov construction are correlated with these initial operators, and there will be some corrections to this that maybe in chaotic theories or non-chaotic theories are quite important, and I think this is a very active research of studies on how to relate those two and how the scrambling from OTOC is related to the Krylov operator and so on.
Just one connected question to that. So OTOCs are, for some systems, they even are considered the false signatures of chaos. They give the false signatures. In scrambling dominated chaos thing, they are OTOCs, the OTOCs. People say they are giving the false signature. So does it happen to the K complexity as well? Like if the K complexity is giving you this signs of scrambling, does it mean the chaos is there, or can we be very sure that the system is chaotic in that sense?
Yeah, I'm not sure. To my knowledge, I think there has been some works on both operators and states sensitivity to this subtle dominated scrambling, and it seems like, guys, maybe you are here, correct me if I'm wrong, like both complexities are not sensitive to that, right? Like if there's chaos dominated scrambling, I think you cannot detect that. So there is some extra property of the system that that will not be detected neither by OTOC or by Krylov complexity, right? Yeah.
Yeah. Okay.
Yeah.
So, if the system is showing scrambling, it doesn't mean that there's chaos.
Yeah, no, there are some counterexamples. Well, of course, both chaos and scrambling, they strongly depend on how you define those two things. But if you agree on some common definitions, there are some counterexamples that you can have scrambling, but in systems that are not chaotic.
Ah, okay. So there are exceptions.
I think in view of time, I think we should end the lecture here because there's another lecture at 2 p.m. So let's thank Pawel again.